What's going on, guys? Welcome to another AI session. So this week has been an exciting week in the AI research arena with multiple releases from both the open source community and big tech. It has been really amazing to see open source models take a lead in multiple benchmarks. For example, Mixtral's new MOE 8x22 billion parameter model was able to take over another open source model, Cohere's Command R+, and they've been doing pretty well, taking over even GPT-4 and GPT-3.5 and Opus as well. So this has been really exciting for me personally to see, because I am pro open source. But what has been really exciting this week is my mentor or my role model released another masterpiece this week called llm.c. So this is basically a training code stack that allows you to train, for example, a GPT-2 model on a CPU at float point 32 in under just 1,000 lines of code written in pure C. So this is really exciting to dive into, and this video will be about going through this code base and following the instructions, and then trying to train GPT-2 on my old iMac 16 GB RAM. So let's see how it performs. So first of all, I've already cloned the repo, and we can go through the README here and see how best we can start training GPT-2. So for example, here we have the quick start, in which the first command was to pre-process the data set, which is this tiny Shakespeare's. You can use either this one or you can use the tiny stories, but I'm using tiny Shakespeare's. So this code basically just downloads the data set and then tokenize it for use later during training. And basically, I've already done this section of the instruction here. So this will save the tokens, it will save the tokens here. For example, the Shakespeare's one will be here. So we'll have two splits, the validation and then the training. So these are raw int32 numbers, that is raw token weights, that are saved in these bin files. Then next up, so he emphasized on how we will be using GPT-2 weight, because trying to train this model from scratch will be very difficult. So we'll be initializing with GPT-2 weights, and then we just fine-tune based on that. And this has been really exciting, especially written in a very low-level language like C. So the next step was to run Python train GPT-2.py. So this basically will allow us to download the GPT-2 weights, and then it will create a small overfit with about 10 iterations, and then this can allow us to actually, I've already done this section as well. So this can allow us to, let's see if I can do it one more time. So as we can see here, so when we run the Python train GPT.py, this will download the model. It's about 124 megabytes, and then it will do about 10 iterations and give us a sample generation from that model, just like that. But most importantly, after downloading inside of the train GPT-2.py, it will save the weights in two files. So first we have GPT-2 124m.bin, which has the raw weight of the model. And then we have another one, this one, debug state.bin, GPT-2 124m, debug state.bin. So this will contain the inputs, targets, logits, and so on. which we can use to later debug the code. So he emphasized that this is very important and useful for unit testing. So, but basically what we're interested in is our 124M, that being this one here. So this is what we will be initializing our training loop with. And next up will be to run make. So this will compile our C code, for example. So if you haven't went through the C code, I recommend you go through it. So it's very, very basic. It's implemented in the most simplest way you can ever imagine. So we have all the stubs needed for training GPT-2 here. Layer num forward, encoder forward, and so on. Forward passes and the backward passes for both, for the encoder. And he also implemented some other algorithms, for example, matrix multiply, as you can see here, both forward and backward, in pure C, and then the attention, backward, and so on. Yeah, so you can go through these. Even I myself am trying to wrap my head around it. Yeah, but it's really, really simple to grasp. So we'll have to initialize make like that. So we just do make train GPT-2. That, I think that's it. Yeah. So this will compile with OpenMP. So you need to have OpenMP installed. This is an issue actually that he emphasized on here. So let's take a look. So he recommend, okay, so somebody had this issue as well, but this one actually fixed my own, because I faced the same issue. So brew install lib OMP will actually fix this, so it will have OpenMP installed, and that should fix the compile command here. And then next up is to, so he gave some, as you can see here, he gave some tries that you can use. This problem is actually common for Ubuntu users, but also Intel Mac, I think. Okay, so here we have here we initialize our train loop. So we'll have to adjust the number of threads here based on our CPU. So my CPU, I think, is, let me see, it's a quad, yeah, quad core, so that'll be 4, so I'll not be able to go up to 8. So let's go back. Okay, so mine, I think I'll just put 4 here. Yeah, so you initialize based on that. And what this will actually do is it will start the fine-tuning loop, and using our Adam learning rate here, and then to later on generate some samples after it has been, after the training is completed. So this is the sample output that we should expect from the training command. Okay, so let's just run this and see. I hope it doesn't crash my Mac. It's a very old iMac actually. Okay, seems to initialize properly. So here we have the parameters of the model. These are the parameters for GPT-2. Maximum sequence length 1024, vocab size 15257, and so on. Number of layers, we have 12. And you can see the batches for the data sets. So number of batches for train, we have 1192, and then validation is that. And the activation is at that point. Let's see if this matches what he had. Okay, yeah. So our activation is the same. Okay, so let's see how the training goes. Let's keep an eye on our GPU, on our monitor, sorry. So Our CPU memory presently, this one looks a bit stable. Okay, let's see the GPU. Holy shit. Sorry about that. We're getting 10 GB. Okay, that's not bad. I have 16 GB, so I think I'm okay. I think this will be really slow for mine because I'm using Intel here. I don't want to try it on my MacBook Air, M2 Mac Air. I'm really scared of that. It only has 8 GB of RAM. So, but let's see how long this one will take. We haven't even started with the first validation loss yet. It's still taking forever to run. Okay, now we have our first validation loss here. Almost the same. Now we have our first validation loss here. Almost the same. So now we'll see our loop. How many training loop? I think 40. Yeah, it should have 40 of those. Okay, that's impressive. Okay, while this is running, we'll have to go through his tutorial. So he made a very interesting tutorial about layer normalization. So here, as he mentioned here, a step-by-step guide on implementing a single layer of GPT-2 model layer normalization. So let's go there and see. So this is it right here. The tutorial actually involves a hands-on step-by-step guide on how to implement layer norm in both PyTorch and in C for no good reason, which is actually interesting when you think of it. So he manually implemented layer norm in C as well. But before we dive into the tutorial, let's first try to understand what layer norm is, which is short for layer normalization. We already have an idea of what a layer is in a neural network, but what does normalization mean in general? So it basically involves scaling values of our input so that they fall within a certain range of standard deviation, which in most cases is 1. And this actually helps improve stability and efficiency during training in general. So layer norm was officially introduced in this paper, layer normalization, it's titled. So the authors here were able to actually compute the normalization for the neurons in a layer on a single training case. So prior to this was batch normalization, in which the neurons were normalized using based on batch size actually. So, but there are some limitations to this, especially when you have variable batch sizes, which is in our case for LLMs here. So here they were able to come up with a way to compute normalization for on a layer in a layer on a single training case. Okay, so as in most deep learning algorithm, it all boils down to pure mathematics. So the layer norm equation is basically this one. So this is a PyTorch implementation. It's a tutorial that he mentioned, but this one is a bit high level. So let's stick with Karpathy's here. So here he explains what the equation actually means. So layer norm right here. So what we are trying to do is to backpropagate on this equation. And as most of you are familiar, backpropagation just involves chain differentiation. So we have to differentiate this equation using chain rule in general. So he defined the terms here. For example, X here is the input and W here the weights. And then here we have element-wise multiplication and next X input as well. And there are two key terms that are actually used in calculating standard deviation, which is the mean and the variance. So mu here is the mean, and then rho squared is actually the variance. So here he implemented it using PyTorch on a very basic level, as you can see here. Sorry, let's see the first one. Yeah, here. So first, this is our forward pass. We have to do both forward and backward pass. And in the forward pass here, we have our input, weight, and bias. And then we apply the input size to our batches, time, and channel, basically. So the first thing here is to calculate the mean, which is mu. So if we look at the formula right here, mu, this one. So the mean will be the average sum of the inputs divided by the number of channels, right? And then there is a shift which helps us calculate the variance. So for the variance, that is rho squared to be that shift squared multiplied by the mean. Yeah, basically. And then lastly, we have to do the inverse standard deviation, the reverse of that. So that will be done by multiplying the variance, taking the square root, sorry, the square root of the variance plus epsilon. Mind you, epsilon is there to actually prevent us from having zero error or having to divide by zero, which will eventually lead to error for the mathematicians right there. Okay, inverse standard deviation of that. And then lastly, we have our normalization, which will be the multiplication of both the inverse multiplied by the shift. And then our output will be the norm multiplied by the weight plus the bias. That's basically what this equation is doing here. Yeah, this multiplied by this plus the bias. And he's storing these variables in a cache here. So which can be used later, and then we output that and so on. So here is a toy example of how the llm forward pass is actually calculated or computed in this case. His point actually is that this is how it's done in PyTorch AutoGrad. So it's actually doing all this at a very high level, and it does so to, for compute efficiency. So it's very difficult to find the direct implementation of layer normalization in the PyTorch code base. And so he was making a point on how high level the PyTorch AutoGrad calculates layer norm in this case. So what he actually wanted to do for the sake of learning is to compute layer norm manually in this case. So which means we'll have to go back to first principles and try to backpropagate through this equation. And in this case, which will mean having to calculate, to differentiate using chain rule on this particular equation here. So he first implemented it in PyTorch here. So first of all, we unpack the variables, for example, our input weight, mean, and our inverse standard deviation. Then storing them into a cache here. And then next, we are recomputing the norm in this case. We'll see why he's doing this later. And then after that, we find the gradient of our bias, which will be this. And then we find the gradient of our weight, which will be that. And then next, we multiply that to find the gradient of our norm. According to the equation, will be this multiplied by this, right? And then lastly here, this is a very important line. So here, we are actually calculating the gradient for the bias and the weights based on the output gradient. So based on the output gradient and the input gradient in this case. So this is what this line is doing. And then lastly, we just return or multiply that by our inverse standard deviation, and then we return the values that we got from there. So as you can see, he has already calculated the differential for each of these terms in the equation, which is very, very cool. Okay, so anybody can understand this. And then next up here is we then call on our backward pass. So for example here, we assign all of these gradient, or we unpack all of this gradient in our backward llm backward pass there. So he made a point why exactly we are recomputing the norm here, because we've already done that in the forward pass, right? Yeah, we've done that here. So why are we still doing it in the backward pass? So here he mentioned that we could have actually done it, compute it earlier and then save that in the cache so that we can reuse it later. So he mentioned that the cache, whatever we store in the cache, is actually up to us. So there was not even a need for us to actually store the mean and the inverse variation, inverse standard deviation in the cache. So that was his point here. But the main difference here is that since the size of our mean and inverse standard deviation is really small, so here it's b by t by c, as compared to our norm, which here is b by t, as compared to our norm, which is b by t by c. So he emphasized the point that this is basically a trade-off between compute and memory. So meaning that since the mean and inverse standard deviation are smaller in this case, so we are trading that off for compute in our backward pass. So this is a very important point, yet interesting to come by. And then next here he gave a toy example, of course, and then emphasized on tensors, as you can see here. So what is a tensor? So it's basically a one-dimensional block of memory, in this case that holds raw data. So for example here, if we have initialized our network like this, so batch is 2 time 3 and then our channel 4. So if we want to assign inputs to this in the form of tensors in this case, so this is what they will look like, just like that. So it's just a one-dimensional array that holds raw values of our inputs or of the network in general. And so he was making a point here how PyTorch computes this one-dimensional array in this case here. So in general, the formula that if you want to retrieve any element from b by t by c, you'll have to compute an offset in the storage that will result in this equation, like so. So if you want to do for input, for output, or for which one again? Yeah, in the backward pass there's one for the gradient of the output and then the gradient of the input and so on. So you'll have to follow that pattern right there in order to calculate, to compute the value for that in that case. So follow up on that. After giving examples, he then implements manually both the forward pass and then the backward pass in C, as can be seen here. So for those of us who maybe are C, are not that strong, but C is very low level and it's self-explanatory. So as you may have learned, in C we have to initialize all the data types for any variable we declare. So in this case, our output is a float and so on. Mean is a float. Inverse standard deviation is a float. We only have for B, T, and C, which are integers. And then next we initialize our epsilon, which helps us avoid dividing by 0. And here we loop through each batch. Inside that, then we loop through each time, and so on. And now for the forward pass, we want to find a position, how do you call it, for each input. So the position of each input tensor, in the tensor, sorry. So here, this is calculated using this method. So this was the point he was trying to make here. In order to compute for each element, you'll have to use, you have to do an offset, which will involve this. So that element offset by the original one-dimensional array, and so on. And then next, so after we've got that, we then save that. Here we're just, setting, how do you call it, a range for our float. And then next we just assign that value to M, which will be our mean. And this is how we calculate the mean, actually. No, this is how we calculate the mean. And then next, we divide by the channel as per the equation. And after that, next will be for the variance, right? So that will be the shift multiplied by this. And then we store that in a variable V. And we calculate the variance this way. After that, we then calculate the inverse standard deviation or the reverse standard deviation as per the equation right here. And then lastly will be, he said seek to the output position. Okay, we've done for the input, now doing for the output, seek to the output position. And yeah, finally we get the mean and the inverse standard deviation, which we will use later in the backward pass, as we've explained. So in the backward pass now, we'll have to seek for our gradients that we've calculated in our, how do you call it, in our forward pass. So the gradient for our output batch will be this, input will be this, and then our input batch will be this, and so on. And then we make use of those values, and as he mentioned earlier, we'll have to recalculate our norm. Where is it? Yeah, we'll have to recalculate our norm, and then to find in the mean of that, then we loop through the channel, and finally we're able to calculate our, how do you call it, normalization for this particular network, yeah. Okay, I'm getting drunk by the code, or drunk in the code. Okay, this is interesting. Yeah, so next on he went on to implement RMS norm, which is another type of layer normalization, root mean square normalization. And this one also he implements manually, as can be seen here. So it's really, really interesting and very, very inspiring as well. So boiling things down to the very basics is where, understanding of the entire concept starts. That's where we get the foundation for that. Okay. So after doing all that, he gave basic summarization of everything, and this can be run. The code can be run using this. So, and we can do also for the C. This one is for the Python one, and this one is for the C, and so on. Yeah. So he actually hoped to continue doing this because it's a developing repo continuously. So the next will be, according to the repo, will be to implement. Okay, he already implemented CUDA, but he's not done yet. Yeah. So we'll have to make use of CUDA in this case to do the same thing. So to train with CUDA. Presently, I think that's what he's working on. So this is actually my mentor's latest masterpiece. See, just within the few minutes we've been talking about this, it's already reached 13,000 stars. So yeah, so that'll be it. Okay, first let's check. I forgot. Let's check our training. Yep, that's it. So we finished training and we got our validation loss to be 4.25. Let's see the requirement here. Okay, here. So the validation loss he got was 4. Okay, we're very close to that. So 4.1 and we have 4.2. And next we'll have to do some generation of that. So the generation, we'll just take this token for example. It's very interesting though. So let's first of all, let's do Python here. Okay, and then we import tick token. I hope this is already installed. And then next, we encode based on our GPT-2. We get the, how do we call it, the encoding for GPT-2. And yep, that one worked. Then next we lambda, okay, decode. And finally we take a bunch of tokens, that is this one, the one that was generated, these tokens, as can be seen there. Let's see what this will give us. And yep, so this is a text from this original bunch of random numbers. Come running away, greater queer with imperial blood, the heaviest. So if you actually take a look at the data set, okay, I think we downloaded it, right? Let me see. Yeah, it should be in here. Tiny Shakespeare, yeah. So it's similar. You can find some similarities here. Let me see if there was anything called imperial blood. No. See if there's any word imperial. Okay. Yeah, so this is basically all that is needed, just less than approximately 1,000 lines of code to train GPT-2 on a CPU for that matter. Quite impressive. Lastly, what we have to do is run a unit test, which he gave here. So this test will actually help us compare the C implementation to that of the original PyTorch, because he wants it to match in this case. And so this can be done with okay, not this command, this one, yeah, not the CUDA one. Okay, So this will actually help us run a unit test on the code, the C code. So it will basically just load our debug state.bin, this one, not this one, sorry, this one, and then it will run forward pass and then compare the logit and the loss to that of the PyTorch implementation. And if it matches, then that's it. So this will take some time, but we're almost there. So as you can see, for each test that passes, you will get the result, in this case. Okay, the last one will be for the training loop. I think this should be about 10 iterations. We can skip to the final one.
Done?
No. Okay, so there we have it. We passed all tests, and yeah, I think that's all for today. Thank you. See you in the next session.